Good evening, everyone. Welcome to today's session, problem solving session, week 9, digital design with Verilog. So, in today's class, we will be seeing the problems for the sequential circuits. So, first we start with the counter. So, counter is a circuit which we will be using to count the numbers like every time incrementing by one or a specific sequence it follows. So, uh, say we start up with a specific at a specific point, say from 5 to a specific uh, number till 9. So we are counting from 5 to 9. It is a counter, or we just count the even numbers to 0 to 4, etc., or odd numbers like 1, 3, 5, or it can have a specific count sequence. And if we say we have a up counter, that means it counts from 0 to uh, the range. If it is like a 4-bit counter, then till 15. And down counter means we are counting from 15 to 0. And we have modern counters, that means the counting sequence will be from 0 to n minus 1 if it is a modern counter. So if it is a mod 10 counter, the sequence is 0 to 9, and if it is a mod 6 counter, it is 0 to 5. So how to design the counter like this? So if we observe from here, we observe that here every clock, if we say, or every time this particular bit is toggling. So again from this to this it is toggling. So this, there is a transition every clock cycle if we assume that the circuit is with the clock, and this if, and we are building this counter using some flip-flop. So here we observe that whenever this transitions from 1 to 0, there is a transition. And here there is a transition in this Q2 bit, only when this is transition from 1 to 0. And similarly, here there will be a transition when there is a transition in this bit from 1 to 0. So that means how will be the design? Say if we are using the T flip-flop. T flip-flop is for toggle flip-flop, and the counting sequence we have 4 bits to, if this we assume, then we need 4 flip-flop for 4 bits. So this should toggle with 1, T is equal to 1, and this will be the clock. So this flip-flop toggles only there is a change in this, so this will be a clock for this flip-flop, and this is our Q0 input. 1. This is our Q1 output, and this will be the clock for the next flip-flop, and all the flip-flops will be in the toggle mode. So T is equal to 1, and this output again will be the clock for this. So this is the counter and the waveform. If you observe, this is the positive edge, rising edge. In this edge, the Q1 will be toggling. So every clock's positive edge the Q0 toggles, and for Q1 toggles when this is there is a transition from 0 to 1. So this edge and this edge, and similarly when this is transition from 0 to 1, there is a toggle here, and similarly this there is a change. But what is the sequence? It is counting to, it's like a down counter. Now here, instead of taking from Q 0, if we take from Q0 complement as the clock, then instead of at this edge transition, the transition will happen in this edge. So this waveform we can observe it is performing the up counter. So coming to the Verilog tool, we are performing the reset operation. So at the positive edge of reset, if the reset is 1, the Q should be set to 0, and this is for the toggle flip-flop. And for the every positive edge of clock, if the reset is not 1 and toggle is 1, Q is equal to complement of Q. Else, when T is equal to 0, Q should be Q. Hence, retain the same state. So we said we need 4 toggle flip-flop, T flip-flop, and this Q0's complement output will be the clock here, and same way this will be the clock, this will be the clock. And T input will be applied, and T is equal to 1 for toggle mode, when anyway that is given as the input to the counter. So here we are keeping the T is equal to 1. So again we are having first part to generate the clock. And this for assigning the inputs and dumping the waveform part to the waveform file. So initially we keep the reset 0, and then we change the reset to 1. This is the output where for every negative edge, uh, it is performing the counting operation. So this is the toggle. The toggle is 1 here, and this is the reset operation. So reset is independent of clock. So this 0 is because of reset, and positive edge toggle. So it is 0, and now it starts counting 1, 2, 3, and then the counting process proceeds. Whenever the reset goes high, it is reset to 0. It is not dependent on the clock, and toggle is always equal to 1 for the toggle operation. Now for the mod counter, let's say if we want a mod 6 counter, so the sequence we need to, the counter will count is from 0 to 5. So we need 3 flip-flops, because till 0 to 7 can be counted by 3 flip-flops. Now at 6, this is 110. When this is condition is coming, we need to terminate the sequence and then again start from 0, 0, 0. This should not appear, and there is a small glitch or this because of the delay. So now here, so how we will be applying, like whenever the clear, we will clear the flip-flops when this condition occurs. So this is like Q2, Q1, Q0, That means when Q1 and Q2 are both 1, and clear if it is active loop clear, there will be a not operation, so that both if we cancel it will be performing the clear operation. That means when this is 1 and this is 1, this will be 0. That means after not it will be 1. It will be clearing the flip-flops. So the clear is obtained with the terminating condition by applying 110. Next, the Verilog code. So we need 3 flip-flops, and we are using the T flip-flop, toggle flip-flop, and this complement is the clock here. And this type of counters we also call as ripple counter, because the clock is the output of the previous flip-flop. And after some delay, we have a reset, which is either it should perform reset operation either if it is reset or when Q1 and Q2 are both 1 1. Because for 1 and 0, for getting when we get 6, the counter should perform the reset operation. So again, coming to the Verilog code test bench. So this is the clock generator block, and this is applying the inputs, and this is the waveform file. So we call this mod 6 ripple counter, and this is on the monitor to monitor the waveform, and this is for the waveform files. So we apply like various reset conditions and monitor the Q value, that is the counter output. So coming to the waveform, at 6, this circuit goes to 6 for small duration of time because of the delay, and from 5 it is going to the 0. This reset to 0. So this is a mod 6 counter. So yeah, here we can observe for after zooming, for a small duration of time it goes to 6. Then it goes back to 0. So it's counting from 0 to, and that duration this remains to be very small. Say for 1 second counter becomes 6. Next type of counter is the mod 10 counter, which is BCD counter because 0 to 9 counter. And so 0 to 9 we need 4 flip-flops, and 10 we should reset the flip-flops. So it should be, this is Q3, Q2, Q1, Q0. We need Q3 and Q1 to be both equal to 1 to reset the condition. So Q1 is Q1 pin, and this is the Q3. If both are 1, we need to clear for the mortar counter. And decade counter, like they are just cascading. So this is for 1's place, 10's place, and 100's place. And connecting it to the source of one display. So here, if we see this is the clock, the frequency of this is, say this is the clock period. This is the clock period, 1 0 pulse and 1 1. So say if it is for 2 seconds. So now this period has come to 4 seconds, and this one is 8 seconds, almost. Sixteen, and if this is incompletely, it is 32. So the time period, this is like say 0.5 seconds, or hertz only it should come. So this will be 0.25 hertz. That means if this is at F frequency, this is reduced to F by 2. This is F by 4, F by 8, F by 16. So this is almost like 1 divided by 32 means 0.3, no, 0.03. Just a second, write this clearly. So this will be 32 seconds. That means what will be the frequency? 1 by 32, which is, says we are calculating this is second, so it should be 0.3125 hertz. And according to this formula, it should be 0.5 divided by 16 hertz, which is again 0.03125. So this also acts like a frequency dividing method. Okay, so any doubts still here? So is there any issue with this way of designing when where we are just trying to achieve the required functionality by modifying the clock? So this is only getting the global clock. This clock is coming from this flip flop. So here there may not be any delay, but slowly, as it's progressing, the delay accumulates, and with the increase in the flip flop, like this MSB flip flop and all, will see a very visible delay. So here also there is a good delay. So we should not play with the clock, but make changes to the circuit. So what is the problem with the ripple counter is that it is not synchronized. It is not synchronized because the counting is not with respect to the global clock. So for this, the example given is that when a student A copies from B with some error and C copies from D. So if this continues up to say 26 students, then the error accumulated will be 26 into error and plus the solution. So this is that propagation delay. So all the flip-flops should take the same clock. And usually we will not keep any other combinational logic also in the clock path. So clock is applied at the first flip-flop, that is the 0th flip-flop, and propagates through the till the nth flip-flop. So the change in the state is used to toggle the next flip-flop. Like the previous change is used to toggle the next flip-flop. That is the clock. So input clock to FF1 is a skewed version of the clock of FF0. So we get the clock plus the propagation delay of the flip-flop. So the ripple counter, it is asynchronous counter because toggling is not with respect to the clock. I like global clock. So what is the worst case settling time? We said that if there are 26 students copying with error, so 26 into error, so error is the propagation delay TPD, and 26 students n flip-flops, so n into TPD, and TPD is the propagation delay of the flip-flop. So when the counter toggles, the toggle signal must propagate through all the flip-flops. And what is rippling? Overall time delay of occurrence of count pulse, and when stabilized count appears at the output. So with the number of increase in the number of count flip-flops, this propagation delay will be appearing significantly. So coming to the Verilog code. So again, positive edge of the reset, we are resetting the flip-flop, and positive edge of the clock, we are performing the toggle operation, and else Q is equal to Q. So now here every flip-flop will have a certain delay. So this is for the T flip-flop. So with this delay, if we observe, then this and design this, run this code for this asynchronous 4-bit counter. So this delay can be observed at the output. So next is synchronous counter. So we have one common clock, and every flip-flop will get this common clock. That is like one single clock to all the flip-flops. So sorry. Need to design and add extra circuitry to make it synchronous. So we will see how to make it synchronous. So Q0 will change every time, correct? But Q1 will change whenever Q0 is 1. Here, here. So this is changing 1, so it is changing. This is 1, so it is changing. So when Q0 is 1. Q2 is changing when Q0 is 1. That is, this is changing. This is 1 plus Q1 is 1. So both. Whereas Q3 is changing when the previous all the 3 flip-flops outputs are 1. So we need an AND gate to achieve this, like Q0 and Q1 are 1. So this will make this toggle. This and Q1, Q0 are 1. Sorry, Q1, Q0 are 1. We will make this flip-flop. And this is the final. I mean, for the output. So to write the Verilog code for this, we need 4-bit, means 450 flip-flop, and here the clock is the same clock, common clock, but the T input is changing. Okay, and this is the output. So instead of changing the clock, now we are changing the T input. So next is binary up counter. So this is synchronous up counter. So if up is equal to 1, it will be toggling this flip flop based on this output. So here we have Q0, Q0 and Q1. So should toggle this. Again Q0 and Q1 and Q2. So toggle this. And that will happen only when up is 1. And if you want down counter, we will have a signal down. Along with that, instead of taking from this is like Q0, now it will be Q0. When we want to perform both up and down counter, we will have a control signal up and down, and we need a multiplexer say that selects between up and down. We need a multiplexer say whenever it is up counter or down counter. If it is 0, then it is up counting, so it should be from Q. 1, it is down counting, so it should be from Q complement. And this will be the input applied to the T flip flop. So this is that multiplexer circuitry. So counter based on shift register, like this has 1 which can be shifted 1 time, 2 time and 3 time. And similarly, this is the value. If we shift it once, again one more shift operation. This came here, this here. One more shift operation, and it is connected in circular format. So this comes here because there is a feedback from here to here. This feedback will be producing this one. So if we need a wall like a clock like design with using the counter, so this if represents the unit place, so it should count till 10, and this 6, so the tens place the 2, 9, 10, and this is representing say 0 to 5, so 6 counter. So this is for seconds, and say this again counts till 10 and this counts till 6. So this is for say minutes, and say this should count till 24. So this is for hour. So again the up counting network. Next, coming to the sequential circuits, the combinational circuit we have represented using the like by using the formal approach, like Boolean expressions, Boolean algebra for simplifying, and circuit minimization using K-map or Q-Minkowski method. So in this way, can we have a design of a sequential circuit in a formal method? So for that, we use FSM, which is finite state machine. So the FSM consists of a combinational circuit, and we have a feedback. In the feedback, we have some registers, so which will be storing the previous state value. So this is the history of. And now we have two types of FSM, which are Mealy FSM and Moore FSM. So Mealy means output depends only on the function of the state. Output is just the function of the state. Whereas for Mealy, the output is the function of state as well as the inputs. So the next state function, if you want to write for the Moore model, okay, I think we'll see this further. So this is the function of the state alone, whereas this output is the function of state and the inputs. And the state means it's the current state. Next, theoretic description. So if S is the like finite states and I is the inputs, like a finite number of inputs, and O we get the finite number of outputs. So this delta represents the next state function, which is the function of the state and the input. But the output is the only the function of the state. So directly what is the state? We get what is the output. So in the mode we can observe that output, it is directly the output of the state. There is no connection with this coming to this flow and then giving the output. Okay. This connection it is not there. That means that's why it is the mode machine. And we have a next state logic, which is a combinational logic. And again we have a combinational logic for the output logic. So this both are combinational logic. And for the Mealy model, the output, which is beta, depends on the state as well as the input. Both S and I giving the will give the output, and for the delta, which is the next state, is the function of state and input, which is similar to the Moore model. And same as the Moore model we described in the set theoretic description, that S is the number of finite states, I is the input, and O is the output, and delta is next state function, and beta is the output function. For this also, this beta is the output function. here we observe this connection. This input is going to the next state function. I mean, this is the next state function which we saw in the Mealy model. This output of this state is going feedback to the input as well as to this, and then we get the output. Same with this next state goes to this input and this one. But extra we have this connection which is the input. So the output depends on, is a function of input and the current state. So synchronized FSM, all storage elements employ a clock input that is set. Okay. What is synchronous? All the flip-flops should use the same common clock. That is the global clock. And FSM, we saw it is a method with which we can design any sequential circuit. So it's a state machine. It's simply another name for sequential circuit. Finite refers to the fact that number of states the circuit can assume is finite. So if we say it is a synchronous, every flip-flop should have the should be connected to the common global clock. So this is the clock, the flip-flop, all are connected to this common clock. So that's why it is a synchronous. Next, we have a combinational logic, and the input goes here, and the output we obtain here. So there is the output logic does not have any. It's not obtained with respect to input, so this is like a Moore machine. And the next state is applied to the storage element and goes into the combinational circuit. So the design procedure, the first step is to write in a high level language like statement. Okay, I can write the next state function here once. So the next state function f1 is the function of the current state, comma, inputs. But output f2 is the function of current state. F1 of f2 because both can be different functions also. Like f1 represents this next state logic, which is a combo logic, and then the f2 represents output logic, again a combination logic. This is a Mealy machine. So for the Mealy machine, this is the next state is equal to f1 and the output f2, which is again current state and now coming to standard procedure for sequential circuit design. So first we describe the problem in description of the problem, and then we model that problem using an FSM, and if required we will perform the FSM minimization, which is an optional step, and then we represent this FSM in a tabular format. Then from that we can derive the number of flip-flops required, and then perform the state encoding. Again, an optional step like optimization of this encoding. Then we derive the next state, which is from the present state and input, and what is the output from present state for Mealy FSM, including the input. And for third step, we derive the combinational function for the next state logic and the output logic. And then finally, we realize the FSM by connecting the next state output logic state register and clock. So which is better, like Mealy machine or the Moore machine? Yes, any answers? Which one is better in terms of, for some logic, in terms of states, maybe Mealy machine may have lesser number of states, but as the input, Mealy machine's output depends on the inputs. Whenever an input changes, even though there is not the clock edge, still the output may change because of this connection. So there are chances of any glitch in the input appearing at the output. There is a possibility in the Mealy machine, but not in the Moore machine, because this state memory will be operating with the clock. So the output will not depend on the any of the glitches in the input. So next we will see some examples. Say step 1, we want a machine like circuit to toggle every clock cycle. So if this is the first step, sorry. So the next step is to represent that in the form of an FSM. So there are two states. Say toggle means off state when this x is equal to 0, and on state when this x is equal to 1. So if we consider Moore machine, so Moore machine, and let's draw the FSM for this. So we have two states, off and then on. So whenever there is a clock edge, it should toggle. And when it, here again, if the clock edge appears, it should toggle. And if x is equal to 0, it is instead x is equal to 1. At initial state, there is not anything specified, so we will take as a simple arrow representing the off state. Like the circuit starts when from off. So when circuit first starts, it starts from the off state. So if we want to represent this in the form of a waveform, can we represent it? Say we have a clock. Like we want to perform the operation at this edge. So From off, it should go to on and back. So it's here the starting, it should be in off state. So the next clock, it should go to on state. So this is a state. And next state, it should be off. In this way, at every clock, it should toggle. So this is the state. What is the output? 0, 1, 0. Now from this, we have to convert to table. So present state, X, and next state. So whenever there is a required edge clock, say 1, the required edge, say 1, to displace I just. So present state, if it is 0, it should go to 1. If it is 1, it should go to 0. The next state is 1, 0, output is 1, 0. So the number of flip-flops required is step 4, 1 flip-flop, and the state encoding, say this one is 0, this is 1. Then we have a D flip-flop which gives the output present state. Say this is the combinational logic, topology. Clock is applied here, and this gives X and N, next state output, which is the input for this. So what should be the X and N? It is complement of P. So his complement is X and also N. So in this way, we can design a controller, say for on and off. Next, if you want to design a D flip-flop. So the step 1 is it should have the, like when NF is depends on the value of the data input. So D should be equivalent to the N. So say we have done this step. Now let's start with the step 2. There are two states, so off, S is equal to 0, and on, so S is equal to 1. So the starting state, say it starts from 0. So D flip-flop, if it is 0, it remains in 0, and if the D input is a starting state, we assume to start from 0. And 1, it goes to 1 state if the input D is 1, and comes to 0 if it is 0, and remains in 1. So the next state is equivalent to 0. So now we have to draw the table. So whatever is the D is the next state. So this is the D flip-flop. So we are directly getting the next state is also D, and X is equal to D. If we are using directly D flip-flop, it will be just the clock D flip-flop. The input should go to combinational logic and come here, so it's directly the N0, and this output is directly S. So before going to the next question, T flip-flop. Any doubts? Okay, to define a T flip-flop, English-like statement, the first step is whenever the next state toggles, every clock, when input T is 1, else stay with the same present state. Next, step 2 is to draw the FSM. So we need two state, 0 and 1. So if we are in 1, 0, if T is 0, it should remain in this, and this is the initial state. And if T is 1, it should perform the toggle operation. Again, T is 0. So what is the present state? Input, next state. So the next state, if input is 1, it should toggle, input is 0, so it remains same. Here it should toggle, here also. So from this, what is next state? Q of T, T complement T of T plus, so this is like Q of T XOR T of. And what is the X? Okay. So this is like having a D flip-flop clock, Q to complement. So D input is T and the. So this one, in the previous class, we have designed using the flip-flop conversion like excitation table and the characteristic table. So here we have used this FSM based method to get the uh, design the same circuit. So if you want to draw it like separately, say we have a D flip-flop. This is the clock to this, the input to this, and this is the output. So this is the S0. This will be going the input to this XOR gate and input T of T. So this M0, which is the Q of T plus 1 next state, will be input for this. and this will be the okay. So next, the Verilog code for the start. We will start with D flip flop. So Verilog code for D flip flop is whenever whatever value of Q will be the D value if it is not in the reset state, and if it is in the reset state, Q will be 0. And this reset is not like synchronized with the. This is the code for the D flip flop. So, if you have any doubts? Okay, so let's go to the Verilog code. So we are designing a FSM using the T flip flop, and I mean we are designing the T flip flop using the T flip flop, and this is the test code. Yeah. Okay, so this is the test bench code. Let's write the so the module TFFSFSM. So T flip flop using the D flip flop inputs as the clock, T and reset, and output is Q. So we need intermediate wires, next state and this state S. So we instantiate this T flip flop D0 with NS, clock, reset and S as the inputs, D, clock, reset and Q. And then we are assigning what is the next state. The NS, which is T XOR S. So this is our next state logic, and the next assign Q is S. So this is the output. So every module end with N. So this is the Verilog code. Next, the test bench. So we are calling this T flip flop T FSM. Here we have instantiated the D flip flop, and this is the clock generation. So here we are applying the value, like initially we are giving T is equal to 0 and reset, and then applying reset is equal to 0. Next, from with a delay of 25 units of time, we are applying the toggle equal to 1. And next 30 units of delay, T is equal to 0. So some various combinations of the input. So let's see the waveform. So at this clock edge, the Q is changing to 1 because the toggle is 1 here, but there is no clock edge, so it remains in the 0. Here, this clock edge, T is equal to 1, so the output toggles. Then at this edge, T is 1, so it toggles. At this edge, T is again 1, it toggles. But usually, if this is a clock curve, we need to maintain the input to be like say T is equal to 1 for this much current here and this much current. This is called T setup and this is called T input. T setup is the duration of time we want to keep the input stable before the application of the clock, and T hold is the duration of the time we should keep the input stable after the application of the clock. It's not like sharp, but this is in the practical when we write codes. When every flip-flop has a certain delay, that time we need to keep maintain the setup and hold time. If not, otherwise there will be a setup or hold time violation and the output will not be uh, in the required state or like. So again, if you want to design a JK flip-flop using the similar procedure, so the first step is the English like statement when output reset. So at k is equal to 1, j equal to 1, reset toggles when j equal to 1, k equal to 1, and both 0 0 it is the no change state, and it is set to 1 when j is 1, k is 0. So next step is to design the FSM. So it is in the 0 state if it is no change, no change, or if it is reset. If it is reset, it should come here. And from 1 to 0, it will come when we are performing toggle operation. And it will go to state 1 when we are performing the set operation or no change. Set or no change. This is the FSM for the JK flip-flop. From this, we have to derive the next state table. So when the input J and K are 0 0, present state is 0, next state is 0. 0 1 0. 1 0 it should be set. 1 1 toggle again set. From 1, if it is 0 0, same state, reset, set and toggle. So any doubts? Yes, any doubts? Yes. So in this way we obtain the next state table, and the next step is to realize the flip-flop. So here we get this next state. It is 1 when j is equal to 1, k is q is 0. So this 1, 2, 3, 4 places. That is like q of t, jk, not 0, 1, 0. So it's 0, 0, 1, 1, 1, 0. Zero, one. So this one and this one. So what is the next state equation? Q of t complement and 1 is j plus q of t k complement. And what is the output? X is q. So with the circuit, D flip-flop input is the from the combination logic, which is generated from j, k and the previous state q, which is j q bar t plus k bar q of t, and we get the next state expression, which is equal to the D flip-flop, and we get the output. From this way, we design the using this method flip-flop conversion. So here we have a D flip-flop D value is j q of t plus k bar. And next, coming to the Verilog code. So we have a D flip-flop instantiation, and then we assign next state and the output. So these are the two logics which we want, a combinational circuit here and a combo logic here. So two assignment and the flip-flop instantiation. So in this way we write the Verilog code in the three parts: next state logic, output logic, and one for the flip-flop instantiation. So what is the next state? J q bar plus k bar q, and what is the output? S is equal to q. So coming to the test bench, we instantiate the like this jk flip flop, then clock generation network, and the input assignment. So we assign various combination of j and k. So next, coming to a counter. So similar way, RS flip flop can also be designed using this kind of from D flip flop with this procedure. So okay, next we will come to a 2-bit counter. So the first step is what we want from this counter. So we want 0 0 1 0 sorry, not 1 0 0 1 1 0 and 1 1. This we want to count, and for each and every one clock cycle, one count value, and this should be repeated. So the step 2 is to represent this in the form of an FSM. So we start with say state A, it goes to state B, next state C, state T, and it comes back to state T. So now this we have to represent using the tabular format, which is the step 3. So we have A, B, C, and D state. So input is like 0, 0. It goes to 0, 1, 0, 1, 1, 0, 1, 0, 1, 1. From 1, 1 again to 0, 0. So next we have to derive the combinational. So what is the N0? It is F0. N1 is 0, 1, 0, 1. Yes, yes. Next is 0, 1. So I have that some if we should fill in this 0, 1, 1, this is 1, 0, 1, 0, this is 0. So if we write this N1, N0, so N0 is 0 complement, and this is what is that? Yes, 0 complement S1 plus S1 is 0, which is nothing but S1. S1 is XOR bit. So how the circuit will look like? We have a state register, say, so it gives two outputs, S1, S2, S0 is using clock, and two inputs, N0, N1, or N1, N0, whatever. I take N1 here, N0 here. So N0 is the S0 complement. And what is N1? S0, S1. S1, S0, XOR gate. So is it clear? Any doubts? Okay. So next we will go to the Verilog board. So we need two flip-flops because we have two outputs taking the input S0, S1 are the output, NS0 and S1. I think this is the input, this is the output, S0 is the output. So this S0, S1 should go as the XOR N1. So N1 will be the input to the flip-flop. So NS1 is S1 XOR and NS0 is complement of S0. And the output is Q1 is S1, Q0 is S0. So this is the next state logic and output logic. Coming to the test bench. We have the same day clock generation network and we are instantiating that FSM, and we this is a counter circuit, so there is no like we just need to change the input, reset. Once reset, it is not performing the reset operation, it will start performing the counting operation. So here the reset is high, that means it is performing the reset operation. So Q0 and Q1 till this edge, it is 0. Now the clock reset is going to 0. Clock edge starts to count 0 1 0 1 1 1 again from 0 0. Here it is going to 0 even though it is not the clock edge because reset is okay. So next, if you want to design an FSM which is like we want a sequence 0 1 1 1 and repeat it. So the step one, say the sequence we want like 0 1 1 1 0 1 and repeating this. So this should be with respect to the clock, every clock this is happening. So the step two, we have to design an FSM. So for example, if this is the clock, then at this posture we want the x to go to 1 and here so 3 clocks it should be 1, again back to 0, this clock edge again 1, so this clock edge 1, this clock edge 1. So it is generating a sequence 0 1 1 0 Okay, 1 2 again one more resource should be 1. So we consider an off state. We want an on one, on two, on three, on for 3 cycles. So x is 0. It goes to this state with respect to the clock when the clock edge, and it goes to, so the x is 1. Here the output is x. So at the clock edge, again x is equal to 1. Again at the clock edge, x is equal to 1. At this clock edge, it should go back to 0. So now this is like extending the system to 3 cycle high laser timer. Let's just see. This is like whenever there is an input, then for 3 pulses it should be 1. So we need to have an FSM for this, where we need a B input, if we consider. Say we now need input, which is B, and output, say X. So again in the off state, X is equal to 0 and 3 on state. So after third one, when clock comes, it should come to this 0. Whenever B, as soon as the clock comes, X goes to 1. Then it remains in 1 for 3 clock cycles. So X is equal to 1. Again clock, X is equal to 1. It is in this off state if it is B complement with the respect and the clock. So this clock we can remove, that is transition with no associated condition. We can remove the clock and the input alone we can represent, and we get the next state table. So from 0 0, when B is 0, it goes to 0. Next state remains in 0 0, but when B is 1, it goes to 0 1, and then whatever is the B with the application of clock, it goes to 3 pulses 1. So in the same way, we can get the expression for this N, S, and X with respect to present state and B, and implement this. These are the D flip-flop and the combinational logic. Let's solve some of the previous year questions. How many flip-flops are required to make a mod 32 binary counter? Yes, 5, because 2 to the power 5 is 32. 2 to the power 5 is 32, and mod 32 means we have to count from 0 to 31. So 5 flip-flops. Next question. What is the terminating condition in a mod 6 counter? Yeah, terminating condition is 110 because mod 6 is 0 to 5, and when this is 4 to 1, which is equivalent 6, we should perform the clear operation. So the terminating condition is 6. Next question. How many states does the decimal counter has? Yes, decimal counter has 10 states. Next question. All synchronous sequential circuits can model using. Yes, FSM. Finite state machine. How many flip-flops are required to implement a more finite state machine with 7 states? So we need 7 states. Yes. 3 flip-flops. So going to the next question. Which flip-flop may reduce the complexity of the next state logic in the implementation of FSM? Yes, JK flip-flop. Why JK flip-flop? Because JK flip-flop have more don't care condition compared to other types of flip-flops. So this characteristics of the JK flip-flop can help simplify the next state logic. Yes, don't care condition. Next question, which FSM output only depends on the current state? Yes, more machine. Next question, an FSM is complete when? Okay, this definition I will just click you. Then next. Yes, first option. All the states of the FSM has a transition definition for all the inputs. Next question, a ripple counter is asynchronous or asynchronous? Or option A, B, C or D? Ripple counter is the counter where first, yes, it is asynchronous. Where the first flip-flop got the output clock from the global clock, and the next flip-flop clock is for the output of first flip-flop, either Q or Q bar, based on whether if we want a up count, down counter or up counter. Yes. So yes. So we will just see what is FSM completeness. So any finite state transition machine, delta is the with respect to state and input, it gives the S. So for all the states of the FSM and for all the types of input, there is a what to say connection. If all the states and all the inputs specify in the transition function. So delta is the transition function. That means if I have an FSM, say 0, 1, so is this a complete FSM? Yes, because S into I, there are two time inputs and two states, so there should be total 4 transition and we have 4 transitions. Another example, so this has transition from 1 1 and 0 1. This has transition from 1 1 1 0 0 0 1 0 0 0 0. So is this a complete FSM? So we have states 0 and 1. Yes, input 0 0 0 1 0 1 1. So number of transitions should be S into I, which is 2 into 4. So total 8 transitions, and we have 8 transitions. So it is a complete. say we have an on state two, on state one, on state three. So this we have already seen this FSM. Is this a complete FSM? Yes, this is not a complete FSM. Okay, so any doubts you have? Okay. So, I will just share in my system. Yes, PPT will be shared in the link, and I think Excel sheet is provided to in that, and this video link also it will be uploaded in the YouTube. So this is model sim. I'm just keeping it in a folder, and to write a Verilog code, new source Verilog. Okay, so we will try maybe one code. format ripple counter. So we need a T flip-flop. So module T flip-flop, and if we write output, register type Q followed by input T flop reset, and always module ends with end, and always at the rate positive edge of the reset. So reset is without depending on the clock, so asynchronous reset. If this reset is equal to 1, that means Q is equal to 0. Next, always at positive edge of clock, begin and end. If it is not the reset, begin. If P not of P, else we should remind me the same sequential elements to non-blocking statement. So this we can save as the T flip-flop dot v, and to compile T flip-flop dot v. So I think we have an error. Okay. And again an error. Yes.
There should be one more end. Q is equal to Q.
Okay.
Line number 11.
Yes. Now to simulate this, we can directly click and right click and perform simulation also. Now if we want a 4-bit counter, say ripple counter clock, we can write here. See, inputs are clock, T and reset, and output is 3 down to 0 Q. So we have to instantiate TFS, T flop 1, Q of 0, T clock, reset, and module for every flip-flop the clock will be the increment of Q of 0, previous flop output Q of 1, Q of then So this we can directly we will do recompilation. Okay. So no errors. Yeah. So now we got this ripple counter. We can simulate this module and we can add a waveform. Clock. We can just force clock. So if we are not writing test bench, directly we can force the values. So reset is the one, right, to perform reset. So one. So we perform the reset operation. So now let's just remove the reset. And now we let us apply the toggle to flip-flop, which is 1. So it should perform the toggle operation. Say now we write this place, this condition, if not reset begin, and we have a delay of 1. Say save, compile, we rerun this. So first we have to apply the clock, force clock, and then reset the slots by applying 1. So we run this. Next we can keep toggle 1 and off this reset. Okay, so at this edge we can observe there is some delay appearing. Let me zoom this. See, there is some delay with respect to here the clock edge has occurred, and with the 0th flop having this much delay, the next flop is having little accumulated delay and followed by the next flop. So there is some delay because of this rippling of the output as the clock to the next flip-flop. So I just wanted to show this too. Yes. So any other doubts? So if no doubts, then we can end today's session. Thank you so much for joining. So I will stop the recording.